Hi everyone. In this lesson, we'll explore one of the most powerful and widely used supervised learning algorithms in machine learning. Support vector machines. Let's dive into the SVM pool. Optimization is the process of finding the best solution to achieve a certain goal. When considering a mathematical function, its graph may contain many peaks and valleys. These peaks represent local maximum, and the valleys represent local minimum. The deepest of these valleys is called the global minimum, and the highest of the peaks is called the global maximum. However, global optima may not always be practical. In real-world scenarios, finding the optimal value within a certain region of a function is a common challenge. In such cases, determining the local optima that best fit the constraints becomes essential. Lagrangian optimization is a mathematical method used to solve constrained optimization problems. Developed by Joseph Louis Lagrange in 1788, this method aims to find the optimal value of a function f x, subject to constraints defined by g x. According to Lagrange, the objective function f x and the constraint function g x are combined into a single function called the Lagrangian. The primary goal is to determine the values that make the first-order derivatives of this Lagrangian function equal to 0. In the equation labeled as number 1 on the screen, the expression f represents the objective function, which defines the primary problem. The expression g in the same equation defines the constraint function, typically outlining a specific region related to the primary problem. The expression alpha indicates the Lagrange multiplier, which combines the objective and constraint functions using a weighted sum approach. The resulting function, combined under the expression L, is known as the Lagrangian function. During the solution phase shown in equation 2, the Lagrangian function is differentiated with respect to all its variables and set to 0. This process reveals the local optimum values of the objective function under the given constraints. Let's work through an example. Suppose we need to find the optimal value of the objective function f x, y equals 25 minus x square minus y square with the constraint 4 minus x minus y equals 0. To do this, we first prepare the Lagrangian function. Next, we take the derivatives with respect to the three variables and set them to 0. By solving the resulting system of equations, we find the optimal values for alpha, x, and y. Substituting these values into the objective function, we obtain the result of 17. The idea of classifying a dataset using Lagrangian optimization was made possible by support vector machines. Support vector machines were first introduced in 1992 by Vladimir Vapnik and his colleague Alexei Chervonenkis. When Vapnik and his colleagues focused on a two-class dataset in their 1992 study, the first question that came to their mind was, if we were to try to find a separator line separating two classes in a dataset in a two-dimensional space, how many different separator lines could we draw? The answer was very easy. An infinite number of separator lines can be drawn. Then the second question came to their minds. Which one is the best separator line for the classes? And of course they realized that they needed to define why the best separator line would be the best. What they developed was a philosophy of classification. Simply put, the line that maximizes the margin between two classes is the best separator line. To make this concept easier to understand, let's use a different example. Imagine two classes as two continents and the line separating them as a channel with its margin. The route of a boat trying to go exactly in the middle of the channel represents the separator line. A person planning this route knows that the most dangerous places are the closest points of the two continents. and thus adjusts the route accordingly. SVM identifies the points where the class data representing the two continents are closest to each other and designates these as support vectors. The next step is simply to find the line that will pass precisely between these support vectors. The objective function in SVM is optimized to maximize the margin between classes while enhancing classification accuracy. In SVM, this function typically involves the weight vector W and bias B that define the linear separator line. The aim is to maximize the margin and simultaneously minimize the model's errors. The constraint functions ensure that the classification boundary accurately separates the data from both classes. These constraints ensure that each sample is correctly classified, thereby capturing the accuracy requirements of the model. Now that we have a three-variable Lagrangian function, we need to analyze its first-order derivatives. When we set the derivatives of the variables equal to 0, especially for W and B, we obtain new equations that allow us to simplify the Lagrangian function from three variables to a single variable. This process yields the single-variable Lagrangian function presented at the bottom. There are various optimization methods used to solve Lagrangian functions. One of these is quadratic programming, the foundation of which was laid by Cukurova in 1939. Quadratic programming, as it is known, must contain a quadratic term. We make our single-variable Lagrangian equation suitable for quadratic programming with a few small transformations. Then we apply the known solution method. The reasons for choosing QP in SVMs are that it is suitable for dual solutions, guarantees a solution in convex problems, and finds a very fast solution. What is meant by dual solution here is finding the equation of both the support vectors and the separating hyperplane at the same time. Kernel functions map non-linearly separable data to a higher dimensional space, making it linearly separable. This enables SVMs to solve nonlinear classification problems. However, there is no single kernel function that can solve all real-world problems. Therefore, it is crucial to find the kernel function that best models a complex, curved, and non-linearly separable dataset. Commonly used and successful kernel functions include polynomial, radial basis function, and sigmoid kernels. This flexibility allows for the selection of an appropriate kernel function for different datasets and problem types. For example, a suitable kernel function can transform two-dimensional data into a three-dimensional superspace. This new feature typically enables the classes in the data to be linearly separated from each other. As mentioned earlier, kernel functions used in SVMs enable the model to learn nonlinear boundaries. Various kernel functions have been identified through numerous studies, each designed to adapt to different types of datasets. The choice of kernel function is based on the characteristics of the data and is adjusted accordingly to enhance classification performance. Researchers who are unfamiliar with the data often rely on trial and error to determine the most suitable kernel function. While this method can be costly, it is sometimes necessary to achieve optimal results. Support vector machines hold significant importance in machine learning and are considered valuable tools for various reasons. The first, SVMs can achieve high accuracy rates even with nonlinear datasets. This is made possible by kernel tricks, which map nonlinear data to a higher dimensional space, allowing for linear separation. The second, SVMs maximize the margin to prevent the model from overfitting. This helps ensure that the model does not overly conform to the training data, which could lead to poor performance on test data. The third, SVMs can be used for many machine learning problems, including classification, regression, and density estimation. They are widely applied in fields such as image recognition, bioinformatics, and text and hypertext categorization. The fourth, SVMs can provide effective results not only with large datasets but also with small ones. The fifth, SVMs are grounded in statistical learning theory, making them well-defined and understood theoretically. This makes it easier for researchers and practitioners to comprehend and apply SVMs. Thanks for watching. We recommend that you attend class for in-class activities.